In this screencast, we're going to talk about doing a stability analysis using something called the Routh Array. Now, since the poles of your transfer function, g of s, determine the stability of the process, you have to figure out a method to see if any of the poles has a positive real part. Now, don't forget, it just takes a single pole with a positive real part to cause the system to become unstable. So this method that has been developed is called stability analysis using the Routh Array. So it holds when this denominator of your transfer function is a polynomial. So consider this polynomial equation: an times s to the nth plus a n minus 1 times s to the n minus 1th plus dot 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 plus a1s plus a0 equals 0. So the solutions to this equation will all have negative real parts if both of the following occur. First, all coefficients a sub I have to be greater than or equal to 0. If even a single one of those is negative, it ensures that at least one root with a positive real part exists. Now the exception is if they're all negative, you just simply multiply by -1 and they will all be positive. The second criterion that has to hold is that all elements in the first column of the Routh array are positive. So the Routh array is constructed as follows. So on the left-hand side here, what you see is a vector which corresponds to the row number of the Routh array. And then you have over here on the right side the Routh array itself. Now, this may not look like much to you, but let's go ahead and step through what each of these symbols inside the Routh array means. So the first thing that you do is you fill the first two rows with the coefficients of the polynomial. So it goes an plus 1, an minus 2, an minus 3, an minus 4, an minus 5, dot dot dot, all the way down until you get to the until you exhaust all the coefficients in your polynomial. So the array ends up with n over 2 columns if n is even, and n plus 1 over 2 columns if n is odd. And if n is odd, the final element in the second element in the final column is a 0. All right. So after you fill in those first two rows, which is pretty easy, the remaining rows get a little bit more tricky. So each element in the third row is composed of elements in the first two rows, and each element is defined as follows. So the A's here, A1, A2, A3, dot dot dot, each A is equal to minus 1 over an minus 1, that's this guy right here, times the determinant of some matrix M sub I. And don't forget what the determinant is, which you can see over here, of a 2 by 2 matrix. Now the way you construct this 2 by 2 matrix is the first column of your matrix is an on top of an minus 1, which would be these two columns of the Routh array here. Or sorry, these two elements of the Routh array here. And that's the first column of this matrix. Now, the second column of the matrix, or the other column of the matrix, is going to be the first two rows of the I plus first column of the Routh array. That's what it says here. Now, it's hard for you to see that, so it's better if this is demonstrated visually. So if you're trying to construct A1, then the M matrix that you're looking for, the first two columns are these two, as always. Sorry, the first column is constructed of these two, and the second column is constructed of these two. So you just go and look at what are those two elements there. And so when you put together your matrix M, it's an minus 1, an minus 2, an minus 3, and the determinant will be determined that way. So in the end, for this element A1, for this element A1, you get this expression, A1 is equal to 1 over an minus 1, that's what it always is, minus 1 over an minus 1, times the determinant of an minus 1, an minus 2, an minus 3. So all of that is minus 1 over an minus 1 times an minus 3 minus an minus 1, an minus 2. And so that is how you would calculate the value of this element, capital A1, which goes in this position here in the Routh array. Now what about calculating other elements? So what about A2? So if I wanted to calculate A2, I would say, okay, this matrix M, the first column is these two, and the second column, if I'm doing A2, would be these two right here. So A2 is equal to minus 1 over A and minus 1, as always, for the row with all the A's in it, for the third row, times the determinant of that matrix M, which in this case the determinant will be an times an minus 5, minus an minus 1 times an minus 4, because that would be the determinant of this matrix M here. an minus 1, an minus 4, an minus 5. Okay, so note that the first column of M is always the same, an over an minus 1, right? So it's always these two elements. And the second column is of that matrix. Basically, you take the element that you're looking at and you look over one column and then the two rows above that. And that forms your second column of the matrix. In addition to that, the denominator here, an minus 1, is always the element in the second row, first column of the Routh array for this third row. Finally, when you get to the end of this row, the last element is 0. The last element in this third row is 0. Okay, so that's the third row, but there are more rows to the Routh array. So after that, the elements of the fourth row are composed of elements from the second and third row, and the general makeup is the same. So all the elements in this fourth row, which I'm going to call bi, so b1, b2, b3, dot, 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 bi is minus 1 over a1, so that would be this element here, and the determinant of a new set of m sub I. So in this case, the m sub I will be the first column will always be these two elements, which in this case will be these two right here. And the second column of that matrix will be, again, the second and third rows of the I plus first column of the Routh array. So if you're looking at trying to find element B1, then that's equal to minus 1 over A1, as always for this fourth row, times the determinant of this matrix here. So here we have B1. So you look over at these two elements here to make your matrix. So the determinant of this matrix, an minus 1 on top of capital A1, an minus 3 on top of capital A2. So the determinant of that array will be part of B1. So if I scroll down just a little bit, B1 therefore is equal to minus 1 over capital A1 times little a n minus 1 times capital A2 minus little a n minus 3 times capital A1. And that will be my value for B1. So I can calculate B1 and substitute it into there. What about for B2? Well, if you notice the pattern here, B2 is going to continue to look the same in the way that we calculate it. So B2 is going to be equal to minus 1 over A1, which is the same for all of the B's, right? You always have that minus 1 over A1, times the determinant of this matrix, where the first two columns of the matrix are these two, as always for the third row. And your second column will be these two. So that would be the determinant of this matrix M, a n minus 1 over capital A1, a n minus 5 over capital A3. And so therefore B2 is equal to minus 1 over capital A1, an minus 1 times capital A3, minus a n minus 5 times capital A1. Okay, good. Now note that every time you go down 2 rows, you pick up a new 0 element in your last previously non-zero column, and you just basically continue this craziness until you run out of non-zero elements. And so that is how you construct the Routh array. Now once you construct the Routh array, you just look down the first column of the Routh array to make sure that every single element in that first column is positive. And if that's true, then you have a stable system. In the next couple screencasts, we'll look at a few examples of how to use the Routh array.